Hey there, let's talk about Dalton's ideas today. For millennia, scientists, philosophers, and sages have wondered what the stuff around us is made out of. Like, what is matter actually made out of? And there's been different schools of thought on this. Leucippus and Democritus, who were Greek philosophers about 500 BCE, came up with this idea that there must be a smallest piece. There would be something that would be uncuttable if you divided it smaller, and they called it an atom from the Greek name atomos, or the Greek word atomos, which means uncuttable. Similarly, about a century later, the Chinese sage Hui Shi stated that there must be a smallest unit of nature. And so we had one group of people who thought that there were atoms, there were particles that you couldn't get any smaller. On the other hand, you had philosophers like Aristotle, who thought you could always make things smaller. There was no tiniest piece of matter. And instead, he said everything's made of air, fire, water, and earth. And for centuries, there was no way to tell which one of these different ways of looking at things and thinking about things was actually correct. The scientist who is generally credited with providing some experimental evidence for which of those two ideas, elements and atoms, or fire, water, air, and earth as the elements, is John Dalton. John Dalton was an Englishman who was born in 1766, and he was working in the late 1700s. He built on the experiments of others, as well as his own experiments, to develop 4 ideas about what matter is made of. Scientists had already shown that there were elements. If you took a material, you could only break it down so far. John Dalton went far enough to say that all matter, those elements, were made of tiny indivisible particles called atoms. So that was his first idea. And the way he pictured those atoms were as like hard spheres, each of a different weight, and each different weight corresponding to a different element. And so if you look at the bottom of my screen here, I have actually a picture of John Dalton's model for his atoms, just hard spheres. His second statement: all atoms of one element are identical to one another, but they are different from other elements. He envisioned what was different about the different elements was their weight, how much each individual atom weighed. And atoms that weighed the same amount were the same element, and atoms that weighed different were different elements. And to support his work, he actually made a list and measured a mass of all the different elements that were known at the time. There were around 30. And for each one of these, he determined what their relative mass was, so how big they were compared to one another. And that's what he thought set them apart. His third statement: in a chemical reaction, atoms are rearranged. They are not being created or destroyed. So whatever atoms you start with at the beginning, you're going to have those same atoms just in a different arrangement at the end. And then lastly, compounds are formed when you take 2 or more different elements and you combine them together in small whole number ratios. So those were Dalton's ideas. But recall what set Dalton's ideas apart from those that came before. He was able to test them. They were supported by experimental evidence. Let's take a look at 3 of the experiments that supported Dalton's work. The first is the law of conservation of mass. The law of conservation of mass was first put forth by Antoine Lavoisier, working in the mid-1700s. He was able to determine that when a chemical reaction occurred, if you measured very carefully, the mass of all the matter at the beginning was exactly the same as the mass of everything at the end. For example, if 5 grams of a compound known at the time as red calx, we now know it's made of mercury and oxygen, is heated, it ends up breaking down and it forms 4.3 grams of mercury and 0.7 grams of oxygen. Notice the mass of everything at the beginning is the same as the mass of everything at the end. Dalton explained this observation with his statement that in a chemical reaction, atoms are being rearranged. Of course the mass is the same. All you've done is rearrange the same existing atoms. The second is the law of definite proportions. If you take a particular compound, it'll always contain the same ratio of elements. For example, in 100 grams of rust, there's always 70 grams of iron and 30 grams of oxygen. Always. In combination with the law of multiple proportions, which we're going to talk about in just a second, this observation supports the ideas that compounds are formed by combining elements in predictable small whole number ratios. About that law of multiple proportions, it's a bit awkward at first glance, but it states that when two elements combine to form more than one compound, the ratios of the second element that combine with a fixed mass of the first element will be small whole numbers. So for example, sulfur and oxygen can combine to form many compounds. 3 of those I've written on the slide. The first contains 32 grams of sulfur and 16 grams of oxygen. The second, 32 grams of sulfur and 32 grams of oxygen. The third, 32 grams of sulfur and 48 grams of oxygen. If you look at the amounts of oxygen, the second compound has twice as much as the first, and the third one, 3 times as much as the first. There's those whole number ratios. And so in combination, this supports the idea that our elements are combining in small whole number ratios, which makes sense if you think about individual atoms sticking together to make the compounds. So what am I going to expect you to know and to be able to do with this information? You need to know Dalton's ideas, and you're going to need to be able to recognize how experimental data about masses of elements and compounds and during reactions can support these ideas. And lastly, you're going to need to be able to apply these ideas to predict things like what's the mass of all the products, what's the mass of a particular element in a compound as we change relative amounts. So you'll be both applying it as well as recognizing how it is reflected.